Hello everybody, thank you for joining me today. This is a repair video on a Marconi 2955A. I have a number of instruments that I'll be doing videos on regarding repairs. This particular Marconi 2955A had an issue with the text on the display being off the edge of the screen. I'm not sure why that happened, and the screen was a little jumping as if it was trying to roll. But basically there are some adjustments inside that you can do in order to correct that and position the text properly on the screen, which I'll go into in a moment. Now I just thought while we've got it apart, we'll have a little chat and a rundown about how the 2955A works and the circuit boards and what they do, and we'll go through the theory of operation and give you a little bit of an understanding of how it operates. I've got the screening cans off as well underneath for the RF section underneath, so we'll have a look at that in detail, along with the service manual diagrams and information as well as to how to calibrate and maintain and repair it. Okay, so the first thing that we've got in the instrument is we have the if we go back to the monitor section a moment, which is what I was referring to at the start of the video, we've got some potentiometers on this side which control the horizontal vertical positioning of the screen, the text on the screen. And all I had was that it was going off like that when I switched it on originally, and then it occasionally jumped like this, as if it was trying to roll like this, going up and down. So I've just brought it back to where it should be. The other potentiometer in the middle here positions the spread of the screen, so the horizontal width, and again looking at that under duplex test, yeah, you can see there that whether you get the screen with the most text, that the L of the level is almost going off the screen, so I might want to just adjust that to there. And then the other potentiometer, which is right at the very end, seems to be at full adjustment, spreads the screen, makes it correctly divided. So that's the focal controls of the CRT, and naturally the positioning of the text on the screen. I've chosen duplex because that's where you get the most text on the screen. Receiver seems to be okay. Have a look at scope, bar charts, etc. They all seem to be alright. Yeah, everything seems fine now. So yeah, I don't know, it just seems it's been stable. I've had it on a couple of hours already just to make sure that it's not something else, and I can't get any other faults to occur on it. So we'll just have a look round inside now then. So the first thing is the power supply section, which is on the rear of the unit, and this particular power supply section in the circuit diagram of the service manual, just put some extra light on there. The power supply board is called AR1. That's the circuit reference on the 2955, and that is a low voltage inverter switch mode power supply. It doesn't work at mains voltage because there's a toroidal transformer inside, which is just there. So this toroidal transformer here has multiple taps on the primary, which are connected to this switch, which is for the low and high voltage range for different countries. And the step down transformer, the toroidal transformer, I think provides around 40 volts AC to this board. And likewise the socket here, which is for the DC battery supply or vehicle supply, 11 to 36 volts I think it is, that's supplied in here as well. And these transistors, which are mounted on this heatsink, are effectively the switch mode element via these transformers, and then you get multiple rails fed out of this then to supply the instrument. So contrary to popular belief, this isn't a main switch mode power supply, it's actually a low voltage inverter switch mode power supply. And so that's the main PCB for the power supply unit and the main power supply. And on the rear of the instrument, this is actually behind another screening cam which goes on the power supply to screen it from noise, etc. And then likewise on the back as well, because we've got the fan there which is spinning, so I'm not going to touch that. We've got the filter rear case which goes on the back, which is held in with just 2 screws on the rear, and we've got the air filters in. These crumble away and are dreadful for deteriorating, but you can replace them. They come out quite easy. They're just held in with little spring clip things, and you can put your own material in. That's air filter material. So that's what's on the back of the instrument to protect all that. Now within the unit, we've got the step attenuator module, which is where the RF signal generator output's fed here, and then it goes through the mechanical relay step attenuator for 10, 20, 30, 40, 50, 60 dB pads before it then leaves to go into what is the RF power attenuator here, which connects to the 75 watt rated N-type plug on the front, and this has got a substrate resistor in it, basically a wideband attenuator resistor, which then reduces the RF level coming in to a very low level to be sent out to the rest of the RF tray underneath and other boards to sample the things like TX power, TX frequency, modulation, all that's read via a sniffing and output on the RF power attenuator. Likewise the BNC socket as well, the low power 1 watt ports fed there for duplex, and again that's got its own attenuator in there. So there's relays in here and then the attenuator pads which then switch in the signal paths in different configurations depending on what you select on the front with the N-type or the BNC. These do have common faults on them where they get dirty and they need to be taken apart and cleaned if the RF level, when it clicks into a particular attenuation pad, if the RF level differs or is totally gone and then comes back and is erratic, then often these need stripping down and taking apart, and then you can do cleaning jobs inside them, so they're maintainable. These are the main boards which do some of the measuring of signals, as in modulation. The calibration is sort of 50-50 on these test sets. We have potentiometers which set up all kinds of different things from AF level outputs and inputs, the scope, the oscilloscope trigger points, and the general audio configuration side of a test set, TX power frequency, modulation depth, modulation deviation, all that can be set on these potentiometers, which is in depth in the service manual of how to do that. So basically, starting from the left is AB6 board, which is this board here. If I refer to my notes a moment, it says that's an AF synthesizer board, is AB6. So that contains filtering. It also has got dividers on it, ranging and filters, and quite a few little bits. So that's the AF synthesizer and D2A conversion. AB5 is a demodern scope board, and that's also got the IF on it and switching for demodulation of AM, FM and phase mod signals. This is the MCPU board, and then we've got the VDU board as well, and then we've got the digital scope. So that's what those boards do. Obviously the monitor, the CRT monitor, is driven off of this board here. This board serves two purposes. One is for the instrument's temperature control crystal oscillator, which is gives a frequency accuracy of the instrument through this, and that can be adjusted with various potentiometers. So if you're setting this test set up to work accurately against another known reference, for example, you can calibrate that TCXO against that instrument, and then obviously you can calibrate the frequency accuracy of the instrument. The rest of the board is made up of the video driver, circuitry and power supply circuitry for the CRT monitor. So we've got the high voltage flyback transformer that provides EHT, I think it's about 12 kV to the display, and then we've obviously got the focus drivers as well, and then we've got adjustments on the board as I've just shown you for adjusting the display. At the bottom down here we've got the main motherboard, which is the interface for all the cards. These cards come out, there are little clips and guides which allow you to take the cards out. They've got edge connectors on them, and then we've got the loudspeaker in the corner, and then obviously at the front section here we've got the keypad assembly motherboard as well. So that's a little rundown of the that. Don't forget as well, there's a fan here, so it's worth, if you get one of these instruments, take all that off anyway and vac it out, because you'll find there's spiders living in there, there's cobwebs, there's dust and all sorts of horrifying stuff in there, so vacuum cleaner that out. And as I say, half of the instrument is calibrated using the potentiometers that's here, but also there is a code that you can enter in a particular sequence, which is in the service manual, that allows you to enter in the software calibration mode. Excuse me, because obviously as well as having the mechanical RF attenuator there, which is a step attenuator, so it's going in steps of attenuation, then we've got basically to also calibrate the RF level which is in between those steps. So each time you hear a clunk inside, that's turning up to the next step, if you like. So as you can hear in a moment, that's one step there, look, another step, and there are intermediate steps as well in between with a slightly softer click. Now in between those clicks we've got a particular control of level between those clicks, which as you can see on the display there, doesn't matter whether you're reading dBm, microvolts, that needs to be calibrated. So that's the other side to the instrument calibration, is we go into the software mode to calibrate the intermediate steps, and that's done when we look at the RF boards. In a moment I'll explain more closely on how that works. But the pin diodes, there's a pin diode attenuator on the signal generator board, which is controlled by the microprocessor with a DC level, and as we adjust the rotary control on the front to a different RF level, in between the steps of the mechanical attenuator, the electronic attenuator, which consists of pin diodes, has a DC control voltage applied to it, and that depends on where we are with the control on here. And that level then changes the attenuation characteristics, the RF attenuation characteristics of the pin diode attenuator, and that's how we get the RF level to change between the physical mechanical steps. So we get a linear sort of control of the RF level, a fine control of 0.5 dB steps or whatever right the way through its level. That's a bit of a nightmare to calibrate on these, because we have to do not only the entire frequency range of the instrument, from basically 400 kHz to 1 GHz in multiple steps all the way across that frequency range, or the dynamic range of the test set, but we also have to do the levels going from basically 0, -120, -130, whatever dBm it goes down to, right the way up to the maximum RF level in 1 dB steps or whatever. So we have to adjust that in the software, and it's a very laborious, long drawn out process, and it takes lots of time to do that. And obviously the digital to analog conversion DAC value levels that linked to that level, if you like, within the memory has to be stored in memory, and then that DAC value then is stored in memory, so that when we dial up on the front a level, or we adjust this, it recalls that level from memory at that particular frequency, and it adjusts the attenuation precisely so that it gives the correct output from these two ports. Otherwise it'll be out of spec. Okay, so if we flip it up, basically on the back here, we've got a number of boards. So this is the RF tray. I've taken the screening cans off already. There's a lot of screws, all the screening cans on, and what have you. So again, it's a bit of a mechanical job when you're getting into them. But basically, if I'm not mistaken, that is AA2's board, and what AA2 does, that's the RF counter. So a sample of the RF signal from the power attenuator, which I showed you on the other side with the heatsink things on it, is fed to this board, and that reads the frequency of the signal, and passes that off, obviously, once it's down converted it, and sends a sample of it off then to the digital board then for frequency readout. This board here on this side, if I can see the reference on it somewhere, it's written on it somewhere. I'm sure it is. Let's have a look. It's got to be on there somewhere. It's just finding it. Let's have a look with a magnifying glass. It is board AA1. That's what that board is. That's AA1. And what AA1 does, that's the RF modulation meter. So obviously when we get a TX signal coming in, it's reading AM or FM modulation, depending on phase mod. And that board consists of the RF side, which is the mixer, oscillator and phase lock loop, PLL. And we can see that already there's a pi attenuator there, an RF signal pi attenuator, where it gets passed off to the frequency counter section as well. So it's obviously sharing the same TX signal that's coming in from the RF attenuator section. And then on top of that as well, we've got potentiometers that we can see here, which will then in the service manual allow you to adjust the setting or the calibration of that. We've got this board down here, and this particular board, if I'm not mistaken, is AA treble A1, is it? Oh, sorry, AA4. That's AA4. So that's the low frequency synthesizer and output amp, it says in the manual. And basically what that is that the RF section for the signal generator, the RF output, and it uses these thick film OM modules which were made by Mullard, like that one down there in the bottom. And basically these modules, along with the relays, tend to be reliable, but the modules, which are these OM modules made by Mullard, they were absolutely shocking with the Mullard modules for failing at one point. And basically the top and bottom of it is that the modules would fail internally, and then they would not produce the right RF level coming out, the right RF level output. And so basically the modules would fail, and then you wouldn't get the right RF level coming out. So you can buy equivalents to these modules on eBay. They are available if these fail, and then obviously, you know, you can change them. Now, we were talking earlier about pin diode attenuators. That's what these are. These are the pin diode attenuators, and they then control the RF level going into the amplifier before it's then passed through then to the output, and obviously fed off then via the step attenuator to the front panel. So that's that section. This board here is the RF Synthesizer Board. So this is basically the phase lock loop, the PLL board, which locks the frequency of the instrument. So when we use a signal generator, we've got different VCOs which are switched in for different frequencies within the instrument, different frequency bands. We also have the filters as well, which are these. I'll zoom in just for a better view, but you might be able to see here that these coils there, L23, L24, L25, etc., these are all switched in with these diodes that you can see with the red bands, obviously, and they are the effectively bandpass filters that are switched in to reduce the harmonic content on the output of those oscillators before they're naturally fed off to the amplifier section. So they pass through, again, another Mullard OM345 thick film amplifier through this connector then to the RF section for amplification again before it's sent out. So that's a rundown of the signal path. These are the synthesizer chips, programmable dividers, VCO control, which then obviously these control inputs are fed to the digital circuitry board, the digital processor board, which then, as you enter in the frequency, test frequencies in on the front panel, it will then set this up to produce the right frequency. Again, we've got another potentiometer here for some calibration of the settings as well. So that's a little rundown of the of that bit. So yeah, if we were to do some testing, for example, to have a look at how good its calibration is, we can do that by connecting up another test set, for example, or separates if you've got a signal generator, or mod meter, separate mod meter, a sine adder. You know, you could have lots of separates, for example, or you could just have a test instrument. So if I set TX, and what we'll do, we'll first of all test its frequency accuracy. So we'll go frequency, say for example 500 megahertz. 500 megahertz. We're sending a 500 megahertz signal to it from a calibrated frequency locked test set, so it's on frequency. If you wanted to, you could adjust it so it's at 0 hertz there, but I don't think it needs it. It's very, very stable, considering this is running on its own internal standard. Whereas the other test set over here is locked to an off-air frequency standard. So, you know, obviously that's more accurate than this in the context of that, and as you can see, the accuracy is very good there. Okay, well we'll put a mod on, mod gen 1 on, and we'll generate a signal. I'll just put the display mod 1 on. We're generating 1 kilohertz at 2.5 kilohertz deviation. So again, we've got a 3 kilohertz plus or minus scope, reading 2.5 kilohertz there. if you wanted to adjust that, there's a potentiometer, one of these blue potentiometers you can adjust to make sure that that reads the right level. The frequency, the mod frequency is reading correctly. If we wanted to test the transmit power level, we've got a known power source such as a 10 watt RF source. It's wideband. I've got one here which I can show you in another video, where it's made by mini circuits, and it's calibrated power output between 10 megahertz to 1 gigahertz, and therefore we could check the RF power reading will be correct, and if not, we can adjust the RF power on the board, the potentiometer, to make that read correctly. So we can test things like tones, for example, as well. If we want to test the tone decoder, so for example, we can select DTMF. I'll just turn that up a second, switch that off. We'll go to tones on here, and we will select DTMF on there, DTMF, and then if I touch a button on here, so that's telling you how it can decode properly with DTMF. We could try, let's have a look here, we could try Sequential Tones, ZVI, I think oh, CCIR. So we could go to Tones on here again, return, Tones, Sequential, CCIR, and I'll send 15789 to it, and then it should decode that, which it is doing. We'll try ZVIE, so we'll go back to ZVIE now and check that tone standard. I'll send the same numerical value to it again. And there we are, 15789, so that works. Tones, Sequential, DZVI, and we'll send the tone to that. Again, reading correctly. Tone, Sequential, EA, another tone standard. I think it's safe to say if it works on one, it'll probably work on the rest of them, because obviously it's using the same tone decoder chip that it does for all of them. So that's all the sequential tones. We could have a look at DCS, for example. So if I set this to DCS, and we're generating an on signal now, so that's there. I'm sending code 777, and I'm getting code 777 as well. So if I change the code to 111 and press enter, then that should read that. Code, I wonder if you have to switch it on and off. There you go. Try another code, enter. That's 555, so it's getting that there as well, so that's okay, that's working fine. And CTCSS, so if I put a 300 Hz low pass filter on, and we go to receives signal output, RF gen output on my test set, and we set up mod gen 3 to basically sorry, mod gen 2. Let's go to tones, CTCSS, and then I'll send a 67 Hz tone, at 500 Hz deviation roughly. So we've got almost 500 Hz deviation at 67 Hz. We can see the frequency there quite nicely. With a low pass filter on, that's low pass filter off. Speech band, so obviously it takes the CTSS off, so that all works fine. And again we can have a look at the CTSS signal. So that section's okay. Now obviously if we were going to do the reverse, we're going to inject a signal out of this to another instrument. We may wish to use, for example, to check the RF output level on here is reading correctly, we may wish to use the scalar network analyzer with the RF head on it. We also have a separate instrument which I have at the other side of the workshop, which I may have featured before, but basically they use the same head on the RF power. So for example, this is an RF power sensor, very sensitive indeed, and we would connect that on the front of here, and then to what is a power meter, because these read microwatts or very low level, so we can check the RF signal generator level right down to its lowest level, and likewise all the range right the way up to its highest level, and then we can, if need be, calibrate the instrument with the software settings to adjust the RF output level on there if it's out by a few dBs here or there. If it's massively out, you know, like 10-20 dBs or whatever, then there's likely to be a physical fault that's causing that, not necessarily a calibration issue. So we can quickly look at that on the spectrum analyzer, and just for most of the moderate output. So I'm just setting the spectrum analyzer up now, which is here, and what we can do, you know, this lamp's always in the way, never ever do they stay out of the way of lamps, do they? Right, so let's have a look here. So we can put the frequency in. We'll have 500 megahertz. We'll have a span. Let's just set that at 1 megahertz for the moment. And what we'll do, right, we'll connect this up, SMA to it, and get it off the end. So we'll connect this to the test set in the RF gen signal mode, and then we'll adjust the RF level variable control along with the spectrum analyzer. So what I'll do is I'll just a bit awkward trying to work one-handed. I'll set the receiver RF gen frequency to 500 megahertz. We'll set the RF gen level to 0 dBm. Okay. Now on here, if I just put the marker, the amplitude, and just attenuate that slightly. Right. So we can see if I just reduce the span to 100 kilohertz. Okay, I'll knock the modulation off, then we don't get the side bands. Right. If you look up in the top left here, we've got the level. I've got them in marker. and adjust that right up to the top. Here we are. So this is the marker level here, and as you can see, we're generating a 0 dBm signal, and we've got more or less that there. Now if I zoom in a bit for you, if I adjust the RF level now on the front of the test set down, so this will be minus 10 dBm, so it's reading minus 10, and then obviously we've got minus. As you hear that click there, one of the common faults that you get is suddenly it'll jump, you know, and that click, instead of going nice and smoothly, it'll go like this, and then go to there really low down out of the wild sort of level, and then jump back up, you know, just as you're trying to go between the clicks. But as you can see, it's keeping it fairly well calibrated there. So it's a neg 30 dBm, which in microvolts is 7.02 millivolts, and then we can keep going down in the dBm scale and really get into, you know, what would be the noise level. So it's neg 83 dBm. We'll need to then adjust the amplitude on the spectrum analyzer as well. So we'll get that up to noise floor's picking up now. And so we're down now almost into the noise floor of the thing. So that's neg 30 dBm according to that. But it can't really read, you see, beyond a certain level. Oh, I know why. Schoolboy error. Right, marker. There we are. Right, so that's neg 80 dBm there, coming out the test set. So it's neg 80 dBm. So that's reading correctly, and keep going down and down and down. So that's like neg 100 dBm on the test set now. It's reading that. But now we can't go any further with it because it's in the noise floor, you see. So once it gets into the noise floor, which is about neg 100 dBm on the spectrum analyzer, we can't go any further. We've reached the maximum sort of, or should I say the minimum RF level that the spectrum analyzer can now look at. And so this is where these come in, because these power sensors are so sensitive that when they're used on these instruments like the microwave test set or the other instrument that I've got the other side of the workshop, which is a separate, which this connects into a Marconi RF power meter, it then will take that, then it would read levels right way down to like neg 130 dBm, and obviously you know, this test set goes right the way down to neg 135 dBm. So that's how we can check the RF output level right the way down. So instruments like the spectrum analyzer are great. They can go down you know, obviously to a very low level anyway, including the spectrum analyzer on this instrument's about the same. That's a better spec spectrum analyzer by far than this one that's inbuilt into this test set, but again, there's only a limit to what the spectrum analyzer can display. Even if I go into setting this up better, which I can do, to try and display instead of 10 dB 2 dB steps, and I alter the resolution, bandwidth and dynamic resolution, and I change all that to the finest minute detail in order to pull out the most microscopic signals, it will still not be able to read down to that level, neg 135 dBm. So this is why we then need to go to the next stage. Once we get down, I think below neg 100 dBm, to this particular thing here. But that just gives you an example of how to check that. Obviously we can set up the mod RF chain level. I put 0 dBm on that again. We're going to inject a signal now into the 2968 test set, and we're going to do that so that we can check the modulation output on the Marconi 2955. Again, if you've got separates, you could do the same thing with a mod meter, deviation meter. You know, if you've got one of those little Raycordana things, you don't have to have expensive or fancy test kit to do these tests yourself. So again, we will set up a TX measurement on here because we're generating a signal from the Marconi test set out, and we're going to get the radio test set here to read that, which it's doing. So I can hear the carrier there, and then if I put the mod on, so I'll say on here, I'll go set mod level on. We've got it at 1 kHz at 1.5 kHz deviation, and then we're reading that here. So let's just have a look at that, and we're reading near as damn it 1.5 kHz. This would depend on the bandpass filters that you've set as well. So if you just put the speech band on 300 Hz to 3.4 kHz, it'll pull that out. And I might want to, for example, on here now, set my mod level to 5 kHz. Set mod level 5 kHz. There. And then we can adjust that down and check the reading on there, saying 4.9 kHz. So as near as damn it. If you wanted to adjust that, you could do. If you were confident that, you know, that instrument was measuring properly, you could do that as well. Same with the modulation for AM. We could do that as well. So we could say set mod level 60%, and now it changes to AM. And then if we do the same on here, we can set whether or not that's AM or FM. We can find out how to do that on this, because it's been a while. Mod type, there we are, and that's now reading 59%, so it's spot on. You know, it's like very, very close to 60% mod there. And that gives you a little rundown of just some of the things that you can check and test when you're doing your own calibrations or whatever. Obviously I wouldn't recommend doing any calibration or adjustments unless you've got known calibrated test instruments that you're using, or that you've more than one signal generator that you could compare against, or you know, that kind of thing. But you get the gist of it, I think. So hope you've enjoyed the video. Thank you very much for watching. I've got some 2955s that don't work. One of them has got no mod on the output when you're basically transmitting into the test set. For example, it doesn't read any modulation, so I'm going to do a video on that, which is a repair. Likewise, I've got a couple of them where when you do the self-test, they fail the tests as they're going down. So this may fail in this case because I've got the screening cans off the bottom for the RF section, so I'm surprised if it passes them all, but you never know. But the other instruments that I've got for repair fail on a number of tests, so we'll go through that in the next videos as to how to repair those, and with the schematic diagrams, etc. And obviously enjoy that video as to there you go, look, it's failed one already because the screening can's off. So when the screening cam's on, it passes them all. So it's odds law, isn't it? Anyway, I'm glad you've enjoyed the video. If you like the video, please subscribe, and keep your eye out for the other videos that are coming up. Don't forget to check out the videos I've already done on the 2955R, the 2968 radio test sets, Rode & Schwartz test sets that I've done features on, Hewlett-Packard Agilent ones, and there'll be many more to come. So catch you in the next one. Bye now.